Hello everyone, and welcome to our webinar. Today we'll be discussing how to improve your PT results on total residual chlorine and fluoride. I am your moderator, Lisa McCombie, and I am the Environmental Product Manager here at ERA. Tom Widera is our Inorganic Product Line Manager and is your presenter. He has 26 years experience in the environmental testing industry, focusing on inorganic and analytical chemistry. A little bit about ERA. ERA was founded in 1977 in Golden, Colorado. ERA was acquired by Waters in 2007, and in 2011, ERA moved into a new 25,000 square foot facility. And there you can see some pictures of our facility. We manufacture environmental proficiency and quality control standards in the wastewater, drinking water, soils, air and emissions, microbiology, radiochemistry, and custom standards. We also have some bulk reagent standards. Take it away, Tom.
Thanks, Lisa, and thank you everybody for joining me today. I know you're all on a busy schedule, and I appreciate you taking time out of your schedule to learn a little bit today about total residual chlorine and fluoride. So as you can see, we've got an agenda signed up for you already today. We're going to discuss the NELAC criteria, the PT limits for both total residual chlorine and fluoride. We're going to show you how to calculate your limits using that NELAC criteria and to be able to use that information for your benefit while you're running your PT samples. We'll talk a little bit about QC sample use and how that can help you with your everyday analyses. We'll talk specifically about fluoride. We're going to talk both about the ion selective electrode and also the ion chromatography method. We'll talk about total residual chlorine. We're going to discuss the Hoch-DPD methods and also ampomeric titration. And if time permits, at the end, we'll have some questions. If we don't have time to answer questions, you're more than welcome to type them in. We'll get them answered and we'll post them on our website for you to see. So the first thing we want to talk about is the NELAC criteria for fluoride. So a lot of people ask me questions on how do you know what PT limits to use for each of the analytes and for the studies. Well, those PT limits are based on what we call regression equations from the EPA. So since the EPA's inception in 1970, data has been collected for all the various analytes and all the methods and people involved in the testing. And with all that data that's been collected, the EPA has established what they call regression equations, which will let us know what the expected recoveries and expected standard deviations are for all the analytes based not only on the methods that are available for that, but all the different people that are running those samples as well. So if you've participated in PT studies in the past, the data that you've collected, the data that you've reported to us and to other PT providers are all put into a big database. The database is then used to establish what we call expected standard deviations and expected recoveries. And then that information is used to calculate acceptance limits. So acceptance limits for both fluoride and residual chlorine in the wastewater or DMR-QA program is based on 3 standard deviations, or what we call a 99% confidence interval around an expected recovery. The confidence interval is around the expected recovery because not every method can recover 100% of an analyte. Some will recover 100%, some will recover as low as 60%. So that's why your statistics are based around the expected recovery. For most analytes, the expected acceptance limits are concentration dependent. And what that means is that for most analytes, it is more difficult to recover something at a lower concentration than it is to recover something at a higher concentration. So as we'll show in a few slides, the acceptance limits on the lower end of a concentration range will be wider than those at the upper end of a concentration range. So the fluoride analyte has a regression equation. So if you see on your screen, you'll see 4 factors, an A, a B, a C, and a D factor. Your A and your B factor are what are used to calculate out your expected recovery. So if we look at our A factor, that's your expected recovery of a percentage in a decimal form. So for fluoride, you should expect to recover about 97% of an analyte. And that's not method specific, but is analyte specific. Then you have your B factor, which is what we call a concentration dependent unit factor for your recovery. Then you'll see a C and a D factor. Your C and D factor are your expected standard deviation. So your C factor is a decimal representation of one standard deviation. So you notice for fluoride, it's about 4.87%. And then your D factor is a concentration dependence unit factor. So that the lower the concentration is, again, as we had mentioned, it's harder to recover, so your limits will be wider. So your expected recovery will be whatever the assigned value is, that's whatever we spike into the sample for fluoride, times your A factor plus your B factor. Then your expected standard deviation will be your assigned value, again, whatever we spike into the sample, times your C factor plus your D factor. So that's how we go and we calculate your acceptance limits. And again, for wastewater and DMR-QA, it'll be a 99% confidence interval. What I want you to understand with that is it doesn't mean that 99% of you will pass the test. What that means is that 99% of the data used to calculate these limits will be in those limits. So for fluoride, our concentration range is 0.3 to 4 milligrams per liter. What that means is that when you receive a PT sample for fluoride, the amount of fluoride in that sample will be somewhere between 0.3 and 4 milligrams per liter. So as I had mentioned on the previous slide, is that the acceptance limits are concentration dependent. So if we take a look at our ABCD factor, our regression equation, we look at what the limits would be if the sample was made at the absolute low end of the range of 0.4 milligrams per liter. So our limits would be 66 to 137%. If we make it at the absolute upper end of the limit, or 4 milligram per liter, our acceptance limits would be 81.1 to 114%. So as you notice, on the lower end, the limits are much wider because it's much more difficult to recover an analyte at the lower end. But at the upper end, your limits are much tighter because, again, it's easier to recover an analyte at the upper end of the range than it is at the lower end of the range. So what does all that information mean to me if I'm running my samples? Well, what we can do is we can take the information we have on these regression equations and we can calculate from that what's called a practical quantitation range. And I'm going to show you how to do that. So what we'll do is we'll calculate out what a minimum value would be for fluoride for your PT test. So we again had mentioned that the lowest concentration we can make fluoride at is 0.4 milligrams per liter. So what we'll want to do is let's calculate out what the expected recovery would be at 0.4 milligrams per liter. So again, our expected recovery is the assigned value times our A factor plus our B factor. So if we use 0.4 as the assigned value, we multiply that by our A factor, which is 0.9748, and we add to that our B factor, which is 0.0156. And that gives us a value of 0.4055. And if you notice when we're doing our calculations, I'm carrying things out to 4 decimal places or 4 significant figures. The reason I do that is because when we go to report our values, you always want to report your values to 3 significant figures. So it's always good when you're doing calculations to use at least 1 significant figure further than what you're going to round your values to. So again, if we were to spike the sample at 0.4 milligrams per liter, you would expect a recovery of 0.4055. So then we want to take the information on our regression equation and calculate out an expected standard deviation. So again, that's our assigned value times the C factor plus the D factor. So if we spike our sample at 0.4 milligrams per liter, we multiply that by our C factor of 0.0487, and we add to that our D factor of 0.0277. So that calculates out one standard deviation of 0.0472. So that's our one standard deviation factor. Then our acceptance limits are 3 times that number, or 0.1416 milligrams per liter. So we can use that information to calculate out what the minimum value would be in order to be able to pass a PT test. So we take our expected recovery of 0.4055, we subtract from that our 3 standard deviations of 0.1416, and we come up with a minimum value of 0.264. So I'm going to explain in a minute where that value becomes important and relevant to us. So then what we can do is, well, let's calculate out what a maximum value would be. So the maximum and the highest concentration we can spike the sample at is 4 milligrams per liter. So we're going to do the same thing. We'll go through and calculate out our expected recovery. So we take the assigned value of 4, we multiply it by our A, add to our B factor, and so what we should expect to get back at 4 milligrams per liter is 3.915. Then again we calculate out our expected standard deviation, so which is our assigned value times your C plus your D factor, and you get a value of 0.2225. So that would be 1 standard deviation. And again, your limits are plus or minus 3 standard deviations, so we multiply that value by 3 and we get 0.6675. So what we can do is use this information to calculate out what the maximum value we could report and still potentially pass our PT, and that would be 4.58 milligrams per liter. Where this information becomes really valuable to us is that we can calculate out what's called a practical quantitation range. So for fluoride, our concentration range from the FOPTs is 0.4 to 4 milligrams per liter. Because we calculated it out a minimum value and a maximum value, your practical quantitation range is 0.264 to 4.58 milligrams per liter. So where you can use this information to your advantage is if you're running your PT sample and you get a value outside of that range, regardless of where we spike the sample, your value is going to fail. So I would not report a value outside of that quantitation range. What I would do is look at my analysis, look at what I was doing in my test, see if I can figure out where maybe something went wrong, try to correct that, and then rerun our sample. So remember that any value reported outside of that range is absolutely going to fail your PT test. What that doesn't tell you is if a value that you're about to report is going to pass. So just because your value is inside that range doesn't necessarily mean it will pass, but what it will do is give us a range where outside of that range we know we're absolutely going to fail. One of the things to help us in our daily operation is the use of QC samples. So QC samples, or what a lot of you know them as certified reference materials, or CRMs, are samples where the concentration is known. That sample is accompanied by a certificate of analysis which will show acceptance ranges. QC samples are a great way to ensure that your process is in control. So if you run your QC samples and it doesn't quantitate within those acceptance ranges, that's telling you something about your process being out of control. You want to do what you can do to check that process, make any corrections necessary, and rerun those samples. So let's start talking about the fluoride samples and the fluoride analysis itself. A little bit about ERA's fluoride samples, which can help you in your analysis, is that ERA fluoride samples are manufactured using potassium fluoride as the source. The sample itself from ERA will contain a mixture of other salts as well, and that's important to know when we're talking about correcting for interferences in both our ion selective electrode and our ion chromatography tests. The sample comes in a 500 milliliter poly bottle, which is what we call a ready-to-use sample. That means there's no pre-dilution of the sample necessary, so the sample can just be shaken and poured for your analysis. And any dilutions of the sample will only be necessary if the concentration of the fluoride being analyzed is above the calibration range of the method being used for that analysis. So let's first talk about ion selective electrode, and in a little while we'll talk about ion chromatography. So the ion selective electrode, or ISE method, is a perfectly acceptable method to analyze for fluoride. In order for proper analysis by selective electrode, the electrode itself must be properly maintained for optimal operation. Fluoride analysis by ISA involves the use of an ionic strength adjuster, or an ISA solution. That solution will contain chemicals that will develop a film coating on the outside of your electrode, and it will cause the electrode to not operate properly. You won't get proper reception, you won't get proper contact with the reference electrode, and it will cause slow response and improper results. So prior to running fluoride each time you run with your electrode, the bottom of that electrode should be cleaned. And believe it or not, the best way to clean that electrode is to use some fluoridated toothpaste. That will help to remove any fluoride and any film on the bottom of that electrode. And make sure when you do that, use toothpaste and not the gel. The gel will actually put a coating on there that will hurt your electrode operation. Best way to do this is to place a small amount of toothpaste on the electrode bottom and just to scrub it with a simple Q-tip. Make sure you rinse that well with deionized water afterwards. Long time ago, a lot of the electrode manufacturers would give you some paper, some aluminum oxide paper to clean the bottom of that with. I'd recommend, if you still have that paper, not to use it because it will eventually scratch the electrode itself. It's also a good idea to change the filling solution on your electrode at least once a month, and more often if you run that electrode analysis more often than maybe once or twice a week. So to maximize our recoveries and our quantitation, it's important that the electrode be calibrated every time an analysis is performed. I've come across people who have told me in the past that they might calibrate once a week, once a month, and then they just run a check standard, which might not be a bad thing to do for your everyday analysis, as the electrode response might change by a few percentage points over the course of a week or 2 weeks. But when you're running a PT test, and as we showed at the beginning, your limits might be as tight as plus or minus 20%, having a drift by 3 or 4% over the course of a week or 2 weeks could be the difference between your value being in the PT limits and outside of the PT limits. And if I missed my PT by 1 or 2%, and I didn't calibrate the same day that I ran my PT sample, I would sure like to have that 3 or 4% back, which could be the difference, again, between being in and out. So I would highly recommend that you calibrate that every time that you run an analysis. You should also run what's called a slope check on the electrode before you use it. So the slope check is run by spiking fluoride at what's called a decade of change, which means a 10-fold concentration change in your fluoride recovery. The electrodes themselves read in millivolts, and the electrode doesn't know what fluoride is. It has a reference electrode and a junction electrode in it that will respond to the fluoride ion, and it will give you millivolt readings. So for any electrochemistry testing, the difference in millivolt readings for what's called a decade of change, or a 10-fold change in concentration, should be 57 millivolts. And most electrode manufacturers will give you a tolerance range of plus or minus 3 millivolts. So the difference in those millivolt readings should be somewhere between 54 and 60 millivolts. This will let you know that your electrode is operating properly. The fluoride analysis by selective electrode is affected dramatically by a large change in ion concentration, because that's what it's reading. So what you want to do is to make sure that you're setting the ion concentration at a constant strength. And this can be done by using what's called an ionic strength adjuster, or an ISA. And it's required for this analysis in order to make sure that you get consistent reading. The ISA for fluoride is called TSAB, or Total Ionic Strength Adjustment Buffer. And it's designed to overcome any large changes in ion concentrations, and it'll set each sample at the same pH value. And that will provide you with consistent results. Remember that I had mentioned at the beginning, especially with the ERA fluoride sample, that it's a mixture of a different number of salts, so the ionic strength of that sample will change with each manufacturing batch. The use of the TSAB will set the ionic strength at the exact same values for each one, allowing your electrode to operate properly. So we can also run fluoride by ion chromatography. Ion chromatography is a much quicker and easier way to measure fluoride. The sample is automatically carried into a resolution column, which then separates fluoride from other ions. The concentration of the fluoride is calculating by preparing a calibration curve. It's very important when you're running a calibration curve that you dilute your sample so that the concentration you're putting on your column is within that calibration curve for maximum quantitation accuracy. Ion chromatography is much less labor intensive than selective electrode, but it does pose other problems. With ion selective electrode, as long as the ISA is added and there are no other issues, then there will be no other issues that will affect the analysis. With ion chromatography, there are many conditions that will affect the analysis of fluoride. First and most importantly, as anybody who's run ion chromatography knows, is the water dip. Fluoride is one of the most smallest molecules of the anions that you will run in ion chromatography. Because of that, it's the first anion that eludes from the column. And what happens is it eludes very near the water dip. So as your column gets a little bit dirty or the back pressure builds up, that fluoride peak will come closer and closer to the water dip. So remember that ion chromatography as analysis is performed by measuring conductivity. Water creates a negative conductivity. So as the water comes out from your sample, you'll see a big sharp negative peak. The fluoride peak will elude very soon after that water dip disappears. When the instrument's clean and the column is new, there's generally very good resolution between that water dip and the fluoride. But again, as the instrument dirties, the column gets dirty a little bit, your resin beds get dirty, or the back pressure builds, that fluoride peak will begin to move closer and closer to the water dip. You'll also notice, too, that your peak starts to widen a little bit, so you'll get some tailing factors in there. So the back pressure increasing will cause the carrier to push the fluoride through the column a lot faster. So as the peak comes out sooner, and in many cases, you'll get co-elution with that water dip. So that can be rectified by changing the support beds on the column, by cleaning the column itself, or if none of that works, replacing the column. Problems with that water dip can also be avoided by diluting the sample being run with eluent. Because what happens there is if you dilute it with the eluent that you're running on your instrument, it removes the water from the sample and will essentially remove that water dip. Certain recent technologies have been developed which use what they call chemical suppression of the conductivity baseline. That chemical suppression will help to minimize that water dip. Without the chemical suppression, the self-regenerating suppressors will generally give you a baseline somewhere of about 25 microsiemens. But chemical suppression now, which is one of the new technologies coming out there, will actually decrease that baseline from approximately that 25 microsiemens down to about 1 microsiemen. And what that does is that essentially will eliminate the water dip. So some tips for running our fluoride analysis. Remember to check to ensure that the value that you're reporting is going to be somewhere between the value of 0.264 and 4.5 milligram per liter, or it's going to fail. When you're running ion selective electrode, most important thing to do is to make sure that your electrode is in good working condition. Clean off the film on that electrode. Make sure that your calibration standards are fresh. Calibrate your electrode every day, and dilute your samples within the working range, the calibration range of your electrode. When running by ion chromatography, make sure that your column is in good running condition. As that column dirties from running field samples, your peaks are going to widen. Your fluoride peak will start to co-elude with the water dip. That'll give you low results. Make sure that you change your beds. If possible, use your ion chromatograph with chemical suppression as opposed to self-regenerating suppression. Remember, again, to calibrate your samples before running them with either technique. A couple of other things to keep in mind. Make sure that you report your values to 3 significant figures. Any PT analysis, the statistics are done to 3 significant figures. Sometimes when I look at the data that's reported for studies, I see people fail simply because they've reported values to an insignificant number of figures. So let's say your upper acceptance limit is 3.25 milligram per liter. If you report a value of 3.253 because you reported the wrong number of significant figures, you can fail your analysis just by doing the wrong number of figures. So again, please make sure you're reporting your values to 3 significant figures. Also, when you're running your PT test, allow time for things to go wrong. Sometimes samples get dropped, your instrument goes down, your electrode breaks, something happens where you can't run the samples. Don't wait until the last couple of days to run your samples. Make sure you allow plenty of time for things to go wrong. Also, make sure that you're running QC samples. QC samples are a great way to work on a continuing, robust quality control program. Not only will that help you to make sure that your process is in control for PT analysis, but for your everyday analysis as well. So let's talk a little bit about total residual chlorine. So total residual chlorine, the statistics are done the same way as they're done for fluoride. Again, it's based upon the EPA regression equations. NELAC has a website, nelac-institute.org, where you can find all that information for yourself. Again, it's 3 standard deviations, just like it was for fluoride. So for total residual chlorine, there's also a regression equation for what we call the high level, or the milligram per liter level of total residual chloride. And you can see the A, B, C, and D factors there. Residual chlorine also has a low-level component, which is in the microgram per liter range. And those limits are what we call hard limits. And the hard limits for total residual chlorine low level are plus or minus 60 micrograms per liter. So to calculate out your expected recovery and expected standard deviation, we would do it the same way we did for the fluoride. So the NELAC criteria for residual chlorine, the milligram per liter level, or what we call the regular level chlorine, is somewhere between 0.5 and 3 milligrams per liter. So we look at our acceptance ranges at 0.5 milligram per liter and 3 milligrams per liter, and you see that the acceptance ranges are relatively similar. So I get people that say to me, hey Tom, I thought you said these are concentration dependent. Well, for most analyses they are, because for most analyses it's much more difficult to recover something at a lower range than it is at a higher range. However, chlorine is one of the exceptions to the rule, and here's why it's an exception to the rule. The majority of people who run residual chlorine run them on Hach meters using the DPD method. Because the Hach meters are designed to run up to a certain concentration, samples are diluted to meet that particular concentration range. So whether we're running a sample at a lower level or at a higher level, since the sample is being diluted for the most part to meet the range of the meters, that the recovery is generally similar, so that the data that's been collected is similar regardless of the concentration range, and it's really method specific and not analyte specific for chlorine, so that you see values that are relatively similar regardless of the concentration range. For low-level chlorine, that isn't the case though, because low-level chlorine is a hard limit. So regardless of what the concentration is, your value is going to be somewhere between, your acceptance range, is going to be somewhere between plus or minus 60 micrograms per liter. So what I'd like to do is do the same calculations that we did for fluoride with residual chlorine. So if we made it at the absolute concentration possible for the chlorine, which is 0.5 milligrams per liter, we calculate our expected standard deviation and our expected recovery. We multiply that expected standard deviation by a factor of 3. We come up with 0.1251 milligrams per liter. So we can use that information again to calculate out an exact minimum concentration that you can report and still pass your PT sample, which is 0.342 milligrams per liter. On the other end, we can calculate out what our maximum concentration would be. So the maximum value we can spike for chlorine is 3 milligrams per liter. So we take that value, we calculate out our expected recovery, we calculate out our expected standard deviation, multiply that standard deviation by 3, and that will give us an absolute maximum value that we can report for chlorine and still pass our PT, which is 3.48 milligrams per liter. So again, we go through and we can calculate out, just like we did for fluoride, a practical quantitation range. So for the regular level chlorine sample, your concentration range is 0.5 to 3 milligrams per liter. So our practical quantitation range is 0.342 to 3.48 milligrams per liter. So a value outside of that range will absolutely fail your PT test. So don't report a value outside of that range. That's telling you that something in your process, again, is going wrong. You want to look at what that could potentially be, fix that problem, and rerun your sample. Again, I want to emphasize that it doesn't mean that a value inside of that range is absolutely going to pass, because you could report a value somewhere near the bottom of that range, and if we spike the sample at the top of the range, the value will still fail. But what this can do is give you a working range of numbers that if you report a value outside of that range, again, you'll definitely fail your PT. And you can actually do this calculation with any analyte that you're going to report in your PT study, whether it's for wastewater, for drinking water, for soils, for air and emissions. So you can go through this and do this with any analyte that you have. So for the low-level chlorine, our concentration range is 50 to 250 micrograms per liter. So that our practical quantitation, when we add in the plus or minus 60, will actually go down from a value of 0 to a value of 310 micrograms per liter. So that's your working range. Again, if you're running your low-level chlorine and you report a value outside of that range, you're absolutely going to fail. So again, I'd like to emphasize the use of QC samples for a robust quality control program. It's a great way to make sure that your analysis on an everyday basis is going to be in control. So if you run your QC samples and you get a value that quantitates outside of the acceptance range, it's telling you that something's wrong with your process. You want to check your process, try to fix what you see that's going wrong, and then rerun your samples. So let's talk about total residual chlorine. All right, we'll talk about the sample itself. From ERA, both your PT and your QC samples are going to come in a 2 milliliter flame-sealed amber ampule. So that sample needs to be homogenized before you take your aliquot out. And I would recommend mixing that sample by inverting the ampule at least 3 times to make sure that you've got a homogeneous mixture. Make sure that the water used for diluting your sample is free both of chlorine and organics. Most sources of deionized and distilled water are acceptable to use. Something I want you to keep in mind, that if you're using distilled water for diluting up your chlorine sample, it's essential to ensure that the still is not a copper-based still. Copper is an interferent for TRC analysis and will cause your results to fall outside of your limits. Another thing that I want to let you know of, and this is something that a lot of people don't know, is that residual chlorine has an affinity to adhere to the small pores which are contained in plastics. So because of that, I would highly recommend not using any plastics when diluting the sample. The most common thing that people use in plastics are Eppendorf pipette tips. So those pipette tips, if you put them underneath a microscope, you'll see that there are very, very small micropores in those. And what happens is that chlorine has a tendency to fill in those micropores and sticks inside your Eppendorf pipette tip, and you'll not end up releasing the entire chlorine sample into your flask when you're diluting it up, and it will cause low results. So don't use any plastics when diluting up your sample. So diluting up your sample, the dilution instructions for that will be 1 milliliter to 1,000 milliliters. So when you're diluting up your sample, take a clean, volumetric Class A flask and fill it with a certain amount of water. Dilution instructions generally tell you 200 to 300 milliliters of deionized or distilled water. That amount isn't critical. You just want to make sure that you're not adding anything to an empty flask. Adding your analyte to an empty flask can cause that analyte to stick to the sides of the flask. Okay? So in diluting the sample, you can use either a Class A glass pipette or a gas-tight syringe. Either will work perfectly fine in diluting up that sample. You want to aliquot 1 milliliter of that sample into the flask and then dilute the flask to your final volume of 1,000 milliliters. Make sure that you shake that sample up real well. Again, good lab practice. And my recommendation is to mix that sample at least 3 times before you take your aliquot out. So let's talk about a few tips and some information regarding chlorine analysis. One thing please remember is that chlorine is very unstable. For those of you that work in treatment facilities, chlorine is what's called a 15-minute test. And it's called a 15-minute test because chlorine not only photodegrades, but it's easily oxidized. And what that means is that exposure to light can degrade the chlorine, it can break down the chlorine, and exposure to air can oxidize or also break down the chlorine. So those samples should be run as quickly as possible after diluting. It's one of the reasons why in your facilities, in your wastewater facilities, you're supposed to run that sample within 15 minutes after your collection. My team here at ERA has done some research on how long that chlorine standard can last until you see appreciable degradation, and it's generally about 2 hours. So please make sure you plan properly for running your chlorine analysis, and run that within 2 hours after dilution. Try not to dilute it up there at the beginning of the day and run it at the end of the day, or especially don't dilute it up one day and try to run it the next day. Your sample from ERA will come with enough sample to do 2 dilutions, so in case something happens and you dilute up the sample and you can't run it right away, that you have an opportunity to dilute that up a second time. Also, most analysis is performed on Hach meters. And those of you that are running those Hach meters know that the Hach meters are internally calibrated. So what that means is that Hach will calibrate them at their facility before they ship it out to you. And their calibration process is fairly simple. The source for the analysis is simply just a light source. And so the way that that's calibrated is Hach will put in a standard of a known concentration, let's say 1 parts per million. That will absorb a certain amount of counts of light, and then that value is extrapolated for your samples to determine what the concentration is. However, certain factors in your lab will cause that calibration to drift over time. As with most light bulbs in your house, the bulb doesn't just go out. The filament doesn't just blow. The bulb weakens over time, so that a 1 part per million standard today might say give you 10,000 counts of light, whereas 6 months from now it may only give you 9,000 counts. So that intensity of the bulb will diminish over time before the filament on the bulb does go. So it's a recommendation to have those meters recalibrated once a year, and I know a lot of states will require that, to have them recalibrated. But to prevent drift from happening and causing your values to be low, I'd recommend at least once a year to recalibrate the meters. Also, for the analysis itself, to make sure that you're not seeing any interferences in there, you want to make sure that you zero the meter prior to running your PT samples. And the way that you do that is to place an aliquot of your diluted sample into your cell. Don't add your DPD pillow yet, but then zero out the scale on that. So that will zero out any potential interference. Then you add your DPD pillow and measure on your meter. So again, most Hach meters will use what they call powder pillows. Those powder pillows have all the chemicals necessary to chemically react with the chlorine in the sample. So as you notice when you're running your chlorine standards, you add your powder pillow, the reaction of the chemicals with the chlorine turns the sample pink to a purple color, and the deepness of the color is based on the concentration. And then your Hach meter is reading the deepness of the color. Generally speaking, that reaction is timed at somewhere between 2 and 3 minutes, depending on the method that you're using from Hach. One thing I want you to keep in mind when doing that, it's a very simple test to do. It's a very high quality test and will generally give you good results. But one thing to keep in mind is what you're doing is you're timing a chemical reaction. So as the chemicals in that powder pillow begin to weather over time, that chemical reaction can take a longer time to complete. So here's what I recommend you do. You want to make sure that the reaction has come to completion. So what you do, add your powder pillow, wait your 2 to 3 minutes, whatever your method tells you to do, and then take your reading at that desired reaction time. As I bet you some of you have noticed in the past, you take that reading, you turn around, you look back at your meter, and all of a sudden you've got a higher value on there. And the reason you're getting that is because the chemicals over time will begin to weather, which means it takes a longer time for that reaction to happen. So here's what I recommend you do. Take that reading. Okay, wait 1 minute. Leave your sample in the cell in your meter. Wait a minute, and then take a second reading. See if that concentration has drifted upward. If that concentration has drifted upward, the reaction hasn't come to completion. So what I recommend doing is take a reading after a minute. If that value has drifted upward, continue to take readings at 1 minute intervals until you achieve 2 consistent readings. So once you've achieved those two consistent readings, sometimes it may take 4 or 5 minutes, then you know that the reaction has come to completion. I get so many phone calls where people say, I reported a low number, but I noticed when I ran that I took a phone call or somebody asked me a question, I turned around and I looked at my meter and the value was higher. And the reason, again, that that's happening is because of the chemicals aren't completing the reaction as quick as they do when they're fresh. It doesn't mean that they're bad. It just means it takes a longer period of time. So what I do is I tell people, well, if you have more sample left over, rerun that test, and I talk to them about the process of waiting a minute and an additional minute until they get their acceptable readings, until they get consistent readings. And then I say, does that consistent reading fall within your range? And 99 times out of 100, they say yeah. So please keep that in mind when running that. So although less common than Hock meters, there is another very good effective technique for running chloride, and that's the ampomeric titration. Most people that I talk to still run the old manual technique. So we're going to talk a little bit about that now. So ampomeric titrator, the manual technique, requires good lab skills by the analyst to achieve acceptable results. Because instead of having an instrument tell you what the value is, because you're putting in a chemical, you have to titrate and use your titration skills. So for the titration method, it's extremely important that the reagent used for the test, which are phenylarsine oxide, that's your titrant, potassium iodide, and acetate buffers, those chemicals need to be fresh. Because just like your powder pillows from Hock, as the chemicals get older, they weather, and they cause a delay in the completion of the reaction. Now for the titration, when you're looking at a delay in the reaction, it causes you to add more titrant to the sample and will cause your values to come back high. So make sure that those chemicals are all fresh. The titrator also comes with a copper electrode that measures your values. The copper electrode will oxidize over time when exposed to air. And you can see that by looking at the copper electrode. When it's clean, is really shiny. And when it's not, it darkens and it's very dull. So you need to make sure that you're cleaning that electrode prior to the beginning of your analysis. When you're doing that, use chlorine-free cleanser, such as a Bon-Ami cleanser. And the reason you want to do that is you want to prevent chlorine contamination. Most other cleansers, like Ajax or Comet, contain chlorine in it, and you don't want to contaminate your electrode with chlorine. But you do need to make sure, in order to get good contact with the electrode and the sample, that it's cleaned. Keep in mind, too, that each drop of titrant that you're going to use in your titrator will deliver about 0.05 milliliters of phenylarsine oxide. The concentration of the phenylarsine oxide is such that each milliliter of phenylarsine oxide will correlate to 1 milligram per liter of chlorine. So every one drop, if you look at your meter, will drop that phenylarsine oxide reading about 0.05 milliliters, so that in each drop. So it's recommended to make sure that you keep your values accurate. What I'd recommend doing is, prior to putting your beaker with your sample on, release one drop of that titrant. Because sometimes when you stop your titrant from coming out, you'll notice that there'll be, a quarter or a half or 3/4 of a drop sitting at the end of the tubing from your titrant, so that you're not actually getting a full drop in your first one. So to prevent that from happening and to help increase, because remember, you're looking at plus or minus maybe 30% for your test. If your chlorine is at the low end of the range, that 0.05 milligram per liter could be 3 or 4% of your value. So release that one drop so that you don't have any phenylarsine oxide hanging off the bottom of your tubing. I'd also recommend, to help the reaction to take place with your potassium iodide and your acetate buffer, that prior to beginning your titration, wait about 15 seconds after you add those. That will give you your time for your chemical reaction to take place. Also, make sure that you're adding your titrant slowly. Sometimes I know we're in a hurry in the lab and we want to try to titrate as quick as we can to get the test done. But you want to make sure that you add that titrant slowing and stir the sample to maximize contact between your titrant and the chemicals in the sample. So a good rule of thumb for adding the titrant is it should be added approximately 1 drop every 5 seconds. That will allow maximum contact time with your sample. Also, once you're close to your inflection point, and generally speaking that inflection point will be about the same for each sample that you run, begin adding the titrant 1 drop at a time. If you keep your titrant valve open, sometimes you'll miss the inflection point and it'll cause you to put too much titrant in your sample, and then you'll overshoot your inflection point. So once you get close, and again, you should know what that is because it's pretty consistent from run to run on your titrator. Stop your titrant and add it 1 drop at a time. Wait 5 seconds, and then if you haven't hit your inflection point, then add another drop. And then once you feel that you've reached that inflection point, add 1 more drop of titrant to make sure that that needle doesn't drop any further. Then you know you're at your end point. So again, some tips for your chlorine. Check to ensure that the value that you're reporting is between 0.342 and 3.48 milligrams per liter. That's your practical quantitation range for chlorine. Or if you're running a low-level sample, make sure that your value is between 0 and 310 micrograms per liter. That's your practical quantitation range for your low-level. Anything outside of those ranges will definitely fail, and you don't want to report that. Make sure that you recalibrate your Hawk meter at least once per year for accurate and optimal quantitation. Whether you're doing the Hawk test or the ampomeric titrator, keep your reagents fresh. And if they're weathering a little bit, allow additional time for that reaction to happen. Again, make sure that you run your samples within 2 hours. Let's remember that residual chlorine is unstable. It not only photodegrades, but it's also easily oxidizable. So that means once exposed to air and light, it's going to degrade relatively quickly. Similar to what we talked about with reporting fluoride, make sure that you report your values to 3 significant figures. Sometimes I see that, and it breaks my heart to see that somebody's failing their PT test simply because they didn't use the right number of significant figures. Make sure that you're allowing time for things to go wrong again. You know, your chemicals can go bad. Your instrument goes bad and somebody quits in your facility, and you don't want to be on your last days of your PT sample when something's going wrong. So make sure you allow time for things to go wrong. And again, it's extremely important to run QC samples. Right. So that's our webinar for today. Again, I know that you have busy schedules and you've got a lot of things going on, and I really appreciate you taking your time out in your schedule to join me today. I hope that some of this information was helpful for you. We're going to collect your questions. I'll get them answered and we'll get them posted to our website. If you need any additional information, up on your screen is the contact information. You have our phone numbers, the times that we're available in our office. Also, if you ever have any questions and you want to type them in, you see our website information. You can type them at info@eraqc.com. Also, join us on Facebook and on YouTube. Thank you, and that concludes our webinar for today.